in our regular computers, when you think about heads or tails, we can actually think about heads as 0 and tails as 1. And that allows us to think of this whole process in terms of regular computing, binary digits, bits, which are either 0 or 1. What's different about a quantum computer is that we can expand that framework. So the quantum computer can manipulate not just 0 to 1 and 1 to 0, but it can use quantum techniques to create what we call superpositions of zeros and ones, which is really about the quantum bit not just being a 0 or a 1, but having some probability of being a 0 and some probability of being a 1. So it seems like that's kind of uncertain and not really very good for doing precision computing. But this idea of being in this fluid state of 0 and 1 is kind of like thinking about a liquid where you maybe have some, two different colors and you swirl it together so that you have, let's say, red and blue all mixed up together. And what's really magical about quantum is that the computer can mix up the two fluid states, 0 and 1, and the colors in this metaphor. But at the end, what's magical is that the quantum computer can actually separate out the fluids perfectly and create whichever color it needs to win the game. And that part is what sounds magical. But it turns out that there are properties of actual quantum particles like photons and electrons where it is possible to do this. Women have always been contributing to physics, but they're not necessarily acknowledged. In fact, it's so common, it's called the Mathilda effect, when somebody else gets credit for women's work. So what I wanted to do is address that issue and shine a light on the fact that not only one or two women, or they're not just exceptional women who have contributed to physics, but there's been so many. In almost every major discovery, there have been women who have contributed, but we don't know of their contributions.
Hello, everybody, and welcome back to Chasing Consciousness. I really hope you're enjoying this third series as much as I am. If you are, please keep helping me spread the word by sharing with your friends. Leave us a 5-star rating on iTunes or subscribe with a bell on YouTube. It really, really helps get this in front of new listeners. And of course, hit the podcast up on Instagram and Facebook to hear all the news and join the fascinating conversation around these topics that we're discussing. Now, today, we have the fascinating new technology of quantum computers to get our heads around. Now, they've been in the news a lot recently, mostly for their extraordinary computing power, should they be harnessed properly, and also in conjunction with the misleadingly named teleportation technologies that it can encode information in a quantum key and then have it appear at a destination instantaneously and unhackably using quantum entanglement. How do these devices actually work? Our guest today, Shohini Ghose, is about to tell us. She studies them as a professor of quantum physics at the Wilfrid Laurier University in Toronto, Canada. She's also a senior fellow at TED, and her TED Talk, A Beginner's Guide to Quantum Computers, has been viewed almost 5 million times. She's a passionate advocate for women in science, which she's just released a new book on and which we'll be getting onto today. And she's the chair for Women in Science at the Natural Sciences and Engineering Research Council of Canada. Now, she is also an author, the author of the 2019 book, Clues to the Cosmos, and her new book, Her Space, Her Time, How Trailblazing Women in Physics and Astronomy Decoded the Hidden Universe, which will be the topic of the second part of our interview today. Now, I have wanted to speak to Shohini about these two big issues ever since I've seen her TED Talks about them and realized that this technology really can change the world. So without further ado, let's go. Shohini Ghose, thank you so much for coming on Chasing Consciousness. How are you today?
I'm great. Thank you for inviting me.
It's going to be a great, great pleasure. So I love to crack in by starting by asking my guests about their first conscious reflections about the world, about existence when they were first coming out of childhood and consciousness was kicking in. What musings can you remember from that time that stick out looking back?
So, growing up as a kid in India, I don't think that we spent a lot of time on questions of existence, to be honest. But I do remember that as a little girl, one moment that sticks out is when Rakesh Sharma became the first Indian astronaut to go to space. And that I remember very clearly because, of course, this was a wow moment, but also that it finally struck me, oh, yeah, people like me can do that. So it sort of made something that seemed impossible more possible. Not that, I've been to space yet, but hey, maybe someday. But also it made me wonder what's out there. What's this guy going to go explore? And of course, I was a kid, so I thought he was probably off on adventures like on Star Trek, but I didn't know any better. But it sort of expanded my mind a lot and made me much more curious than I was before. And then over the years, that led me, of course, to explore more about the mysteries of the universe. And I think that's been a driving force, as in just curiosity. What's out there? I think that's kind of a human thing where, you see a door and you want to know what's behind it. So that to me is always a compelling reason to study what I do, which is all the doors of the universe. I want to open them all.
Yes. And it's not just a very human thing. It's a very, very scientific thing, isn't it? That insane curiosity, that desperate need to know. So, Shohini, before we get on to your most recent book, Her Space, Her Time, and this important theme of women in science, let's get into our main subject for today's conversation, the development of quantum computers. Now, I know you're a TED fellow, but all the same, 5 million views for your beginner's guide to quantum computers is quite a count. What an interesting sign of the curiosity and interest in this topic. What is a quantum computer? And Shohini, if you wouldn't mind, maybe you can start with the coin flip game from your TED talk, because I just think it's the best way to introduce this principle, which is really completely different from anything we know from traditional computing, isn't it?
Absolutely. I'd love to. So quantum computing is not at all like everyday, current computing that we now call classical computing, just to keep it separate from quantum, because it's actually a completely different style or framework of computing itself. And so an example that I often use to show just how different and bizarre it is this little coin flip game. And it's pretty simple because it's basically a two-player game where each player gets to flip a coin, and it's random. You can choose heads or tails as your outcome, but you don't say what is the outcome. You can you may know you don't actually look at the coin. And at the end of the game, each player goes a couple of times, and then at the end of the game you see what the outcome is. And if it's heads, one player wins, and if it's tails, the other player wins. But it's all 50-50. It's a coin flip game. So, of course, if you actually played this game, you'd have a 50% chance of winning at the end of the coin flips. However, if you play this game against a quantum computer, and the quantum computer gets to use quantum rules to also flip the coin, then the quantum computer will beat you 100% of the time. So that sounds completely bizarre, like cheating or something or magic. But in fact, that's only because the quantum computer can actually use quantum kinds of approaches to flip the coin. And it's so different from the normal flipping that this is why you can imagine that quantum computing itself, which builds on the kinds of techniques that this quantum computer would use for coin flipping, actually is very, very different from standard coin flipping, which is based on standard flipping of zeros and ones. So it's a very small example of the framework that quantum computing is built on, which is very different from the regular computing framework.
But help us understand this very quantum, non-binary, probabilistic uncertainty question. How does the computer manage to untangle this non-binary state in the correct way to win at the end? Surely it would need to know what we had got to come out always as the winner.
In our regular computers, when you think about heads or tails, we can actually think about heads as zero and tails as one. And that allows us to think of this whole process in terms of regular computing, binary digits, bits, which are either zero or one. What's different about a quantum computer is that we can expand that framework. So the quantum computer can manipulate not just 0 to 1 and 1 to 0, but it can use quantum techniques to create what we call superpositions of zeros and ones, which is really about the quantum bit not just being a 0 or a 1, but having some probability of being a 0 and some probability of being a 1. So it seems like that's kind of uncertain and not really very good for doing precision computing. But this idea of being in this fluid state of 0 and 1 is kind of like thinking about a liquid where you maybe have some, two different colors and you swirl it together so that you have, let's say, red and blue all mixed up together. And what's really magical about quantum is that the computer can mix up the two fluid states, 0 and 1, and the colors in this metaphor. But at the end, after your turn is done and you've just done the standard sort of flipping, which is about separating the colors, where you can't really manipulate and swirl colors. What's magical is that the quantum computer can actually separate out the fluids perfectly and create whichever color it needs to win the game. And that part is what sounds magical. But it turns out that there are properties of actual quantum particles like photons and electrons where it is possible to do this. So that's why it works.
And that makes sense regarding quantum phenomena, but it still doesn't explain to me personally, sorry listeners if I'm missing a trick here, it still doesn't explain to me personally how it can win, because doesn't that mean that it needs to know what we had?
Well, it doesn't, because the way that these sort of what we call quantum operations or quantum gates, if you like, things like switching a 0 from 1, 0 to 1 and 1 to 0 and so on, these kinds of operations are what we call gates. The quantum gates are such that no matter whether your the outcome of your flip was 0 or 1, it doesn't matter in either situation, because it can sort of manipulate the 0 into a combination of 0 and 1, or a 1 into a combination of 0 and 1. It doesn't care which one you start with. Right. So it's not that it needs to know, because regardless of what you do, it can create exactly the combination that it can then unwind. So,
well, this is probably why they call it quantum strangeness, which I'm sure
really is strange.
I'm sure we're going to talk more about that. So, as so often about these situations where technology comes before a complete understanding, and really we haven't fully understood quantum mechanics yet. Listeners, this, as you know, is something we're really trying to get to the bottom of on the show. But it's interesting that the technology it runs ahead, doing the best it can with these amazing phenomena, even if we don't understand them. And that brings me on to the nuts and bolts of these devices. Now, quantum states and systems are notoriously sensitive to outside macro scale interference. So can you describe how such a sensitive quantum system is integrated into the device itself, and then how the behaviors of these particles are harnessed into computing power, as we would understand it?
That's a big question, and it's something that scientists and engineers have been wrestling with already for a couple of decades. You're exactly right that when you have a quantum particle like an electron or a photon, we want to be able to control all of its properties individually, and then make each of these quantum particles, or quantum bits, qubits is what we call them. Each qubit, we want to be precisely controlling and somehow manipulating it to interact with the other qubits in order to do whatever calculation we want to. In order to do that, there are ways to connect these particles through various kinds of interactions, like magnetic interactions, electrical fields, and electrons have charge, for example. Photons have polarization properties. These are the kinds of properties of these particles that we can manipulate. using magnets and all of our, technologies that we already have existing. But we have to do it at an individual precision level, which is very hard. And at the same time, as we try to make these qubits connect to each other, we also don't want them to be interacting with anything else that is not a qubit. Because when the qubits connect with each other, they form this wonderfully interconnected state that we call entanglement. And that kind of powerful connection between all the different qubits is actually more of a resource than we currently have in our regular computers. So entanglement is a good thing. When the qubits are talking to each other, we can harness that to speed up our calculations. But the problem is that if qubits can get entangled with each other, they can also get entangled with things outside of the computer, such as some perhaps passing stray particle in the universe, and they go and talk to that and get entangled with that. That's what we call noise. It destroys the quantum computer itself, meaning the computing will not work. So in order to avoid that, we have to play this balancing act where we try to connect the qubits to each other in a very precise, controlled way. But at the same time, we try our best not to allow these quantum bits to talk to anything else that we're not controlling. And that's hard because who knows what what the environment is doing at all times. And because of that, it becomes really challenging as an engineering problem. One thing that is done with current computers that are that are based on using superconducting circuits. One thing we can do to make sure they don't actually connect with anything that causes noise is to keep them extremely, extremely cold. So there's a huge refrigeration process that has to be done all the time to make the calculation work. And we're not talking about, how our laptops sometimes overheat. And then, the fan goes on and you have to wait and restart. So we already know this problem, but what I'm talking about is much worse because the quantum computers, when we say they overheat, that means if they get above basically a few millikelvin, which is colder than outer space. So if they heat up even the tiniest bit, it's really bad for quantum computing. So this is the challenge. However, there's lots of very, very smart scientists and engineers working on the problem. And many of the large computing companies, IBM, Google, Microsoft, everybody's now very focused on trying to address these challenges. And the final piece I want to mention is that if there are errors, in fact, there's an entire sort of framework for how to correct quantum errors. It hasn't been actually implemented yet, but as these computers are scaled up and engineering gets better, part of what will be done is to incorporate this kind of quantum error correction into the system, and hopefully that will eventually lead to a stable, robust machine. But we're not there yet.
So just to clarify, Shohini, how do we actually go from the interaction between these entangled particles to what we would think of as processing power? Like, how does the computer actually harness that interaction to make calculations?
So it's a little bit hard question to get into without going to mathematics, unfortunately.
I know, I'm sure it's going to be technological, but just the concept.
Well, there are many pieces to, quantum computing that all have to come together to be able to execute a task in a way that's better than what we can do with our regular computers. And in fact, there's only a few known tasks that we know for sure a quantum computer would do better. And in those tasks, what happens is that the quantum bits, the qubits, as I was saying, they interact with each other, they become entangled. Combined with that is this idea of each of the qubits being in a superposition, meaning they're not specifically 0 or 1 precisely, because if they were, then that would just be like regular computing. So what we're doing is we're creating these wonderful fluid superpositions of 0 and 1 at the same time. And then we're getting all of these fluid qubits to talk to each other and create this giant entangled superposition where that allows in a way you can think of it like a landscape where there are all these possible combinations of zeros and ones, and in that landscape somewhere one of those combinations of zeros and ones is the correct answer to our task or our calculation. And what we're trying to do is create an algorithm so that all of the combinations, the entanglement, the superposition, this giant state, which we call a wave function. We want to control the wave function in such a way that all of that landscape and all the possible answers are explored. And in the end, we cancel out all of the wrong answers and make that giant fluid wave function flow towards the right answer, so that the probability, everything is probabilistic, but the probability of the right answer is somehow maximized. And that's the control piece that we have to do through whatever quantum operations and gates we do. And we do know how to do that for certain tasks, such as factoring very large numbers, which seems like a random math problem, but in fact, it's very important because it underlies all of our encryption techniques today. So if we could build a quantum computer that's large enough, then we already know what we would need to do to manipulate this giant fluid quantum wave function with exactly the right operations, so that we can get the final answer, which would be the two numbers that are the factors of some large number. So that's an example of a task we do know how to do.
Well, and this brings us on to the applications, which is what everyone's so excited about and why the investment's flowing so well at the moment. I mean, just as exciting as how it actually works are the applications that this tech can offer. Let's start with encryption, as you mentioned it. Information can be encoded using a quantum key, and the quantum uncertainty makes it impossible for hackers to copy that key. Tell us how this will work and how it's fundamental to this really big idea at the moment of a quantum internet that's really getting a lot of investment.
Yeah, sure. So our current encryption, as I was mentioning, is based on some kind of a hard math problem. And the idea being that something like factoring, which we know to be a hard math problem, is a good sort of mathematical problem to base encryption on, because if an eavesdropper or a hacker wants to hack into the information that you are encrypting, they would have to solve that hard problem. And if it's hard for you, it's hard for them. And I talk about computationally hard, which means that your data hopefully is safe. But of course, if they build better computers, then eventually maybe the hacker will be able to hack into your information because they can solve the math problem. Or maybe somebody discovers a very fast, efficient algorithm for that particular math problem, and then we're all in big trouble. It could happen. Nobody has proved for sure that something like factoring cannot be done easily. It's just we don't know of a particular way to do it. But maybe in the future, some very smart kid will figure it out. Who knows? But if we move away from using hard math problems, we can try to think about using quantum physics itself instead of mathematics. Let's try to use physics for encryption. And that's the idea behind something called quantum key distribution, where the information for creating a secret key is sent using these individual quantum particles that are now in this superposition, where they have some possibility of being 0 and some possibility of being 1. And this kind of quantum uncertainty is built into quantum particles, meaning even if you tried, you can't actually precisely know everything about a quantum particle. That's just not allowed. It's a law of physics. So if a hacker tried to actually copy quantum information and precisely tried to clone the information, there's actually a theorem called the no cloning theorem in quantum theory, which says that a hacker cannot precisely copy everything. And that's what's really powerful, because it means that that's fundamentally built into the laws of nature. Meaning, no matter how powerful that hacker's computer is, no matter how many resources they have in the universe, no matter how far forward we go in time to even better technologies, unless we break the laws of physics, quantum information cannot be copied. Or maybe if somebody proves that quantum theory itself is wrong, which is not necessarily going to happen. Maybe, but it's possible.
And how does that relate to this idea of a quantum internet? But roughly, what is a quantum internet, and why is this encryption question so crucial to it?
Well, a quantum internet, as the name suggests, would be some version or perhaps an addition to our current internet, which is all about, of course, sending and receiving information for various purposes. But the quantum internet would be a sort of larger, perhaps more complex version of it, where we include channels for using quantum information to send and receive messages. So because quantum has this possibility of enhanced encryption, maybe you and I wouldn't see much difference when we send emails. But on the back end, perhaps there would be a quantum key distribution system or some other kind of quantum security or quantum process running so that the information is either being transmitted more efficiently, or there's some authentication being done in a quantum way, or there's enhanced privacy or enhanced security. So these kind of features, which are something that we all need to focus on even in our current internet, there are ways to try to build these into our current internet. We would want to be improving them and enhancing them. And so if we could do that using quantum processes, then that would lead to sort of like another layer on top of our current internet. I don't think we're going to get rid of our current internet. It's just going to be enhancing what we have. And that is broadly what people mean when they say quantum internet.
Right. And you mentioned efficiency there, and that brings us on to processing power. Now, recently it's been in the news that quantum computers have been used to help develop technological and manufacturing solutions. In the case I read about last week, it was the development of a new type of material to replace glass that reflects heat off windows, helping with climate change issues whilst letting light pass in, minimizing here, in this case, the need for air conditioning. And here, the quantum computer helped run millions of possible combinations of molecules to find the most efficient one in a fraction of the time that even a supercomputer would take. Now, in the past, you've given the example of development of medicines being done in quite a similar trial and error way. Tell us how this application has changed the playing field from our usual sort of supercomputer, machine learning, computer-assisted research.
Yeah, I think one of the more exciting possible applications of future quantum computers, not the computers we have today, because current quantum computers are not necessarily at the scale we need to be able to solve very large problems, needing large numbers of qubits. But even a mid-sized quantum computer would be interesting because it could be used exactly for the kinds of problems you are mentioning, what we call quantum simulation. The idea being that, let's say you are trying to calculate all of the properties of some kind of a molecule, whether it is for, building a better type of glass, as you described, or anything to do with materials design, or to try to understand how this molecule interacts with, biological systems, perhaps to develop things like drugs, or, there are so many possible kinds of applications, or even a material to build better solar cells and so on. All of this is about understanding the chemistry of molecules and different types of structures. And to do that, currently what we do is we try to model them on our current computers. Of course, we do experiments in the lab, but we also try to calculate what are the energy properties and the different, kinds of structures that these molecules can interact with. So in order to do that, it takes a lot of computing power, because you have to take every single electron in the molecule and all of the nuclei and the protons and the neutrons. And it's this giant number of particles, and all of them you have to precisely be able to describe in your computer, and then keep track of them all. And then you have to solve these equations, which basically are quantum physics equations. So we're trying to use our classical computer to encode all of that and then model it somehow and calculate things that are really quantum properties. Instead, if we used a quantum computer, then we could encode the information much more efficiently, because the computer itself has those properties. It's operating using the same properties. So it's like mapping one system onto another quantum system. And that would be much more efficient and would run in a way that is, in a way, more natural. So it's sort of like thinking about, when you're trying to build maybe a soccer ball and you're only given square pieces, right? Eventually, you could kind of make something like a Lego set where you have only square pieces and you're trying to make a nice round soccer ball, but you can't quite get there. I mean, you can get roughly a nice sphere, but you're not using the right pieces because they don't have the right shape. It's just not a natural fit. Instead, if somebody gave you a box with lots of curved pieces, then that would, of course, help you much more efficiently. You'd still build the same soccer ball, roughly, but it would be closer, more accurate, and it would take less pieces, so it'll be more efficient. And that's the idea behind a quantum computer trying to model quantum systems like molecules. The pieces and what you can use to encode and calculate the quantum mechanics of the system are much more naturally a fit. Therefore, there will be efficiency in it. So that's why it's very exciting.
And the last application I wanted to talk about is not necessarily directly about quantum computers, but it's about entanglement. I mean, it's provocatively named teleportation of information via quantum entanglement. And it's been in the news a lot the last few years, with the first instantaneous teleportation of information between two chips, completely unconnected chips in a lab in Bristol. And then secondly, with China's staggering achievement of teleporting information between a ground station and a satellite over 100 kilometers high in the atmosphere. Now, listeners, we've covered entanglement in detail in the first series with theoretical physicist Chris Fields. For anyone who wants to sort of sort the wheat from the chaff here, because it's often overinterpreted, this concept of quantum entanglement. And here on the show, we're trying to do our best to sort of help separate the woo from what's genuinely interesting and genuinely strange. Shohini, personally, I think this is a misnomer to call it teleportation, because it conjures up the image of Star Trek, like your childhood thought, rather than this idea of just encoding information. But tell us how this teleportation actually works, how it relates to quantum computers and encryption, and eventually secure quantum communications.
So quantum teleportation is not Star Trek teleportation, which actually makes me sad, because I love the idea of Star Trek teleportation, and I wish I could just transport all around the world, for example. But the difference is that quantum teleportation is not about physically sending material, which for example, humans are made of. It's about sending information, these combinations of zeros and ones. And the second piece is that it's not instantaneous, actually. So there is a time lag, in the sense that it takes time for light to travel from one location to another, and you can never beat the speed of light. So light travels very fast, so it could be very fast, but it's not instant. That being said, it's still a very, very fascinating idea. And the reason we call it teleportation is because what's happening is, let's say you want to send a message, some combination of 0 and 1 from point A to point B. The teleportation process is that you can actually send the superposition, which is quantum information, which is not even a certain specific message. Remember, it's this fluid quantum superposition. You can actually send that message from point A to point B in such a way that the information is basically deleted or destroyed in location A, and it's recreated in location B. But you don't actually have to send it physically, in the sense that the actual message itself, what's encoded in that quantum bit, that message is not actually sent. The only thing that is sent from A to B, Alice to Bob, is that Alice has to basically call Bob or email Bob and say, I'm sending you a message, and you have to set your teleporter device to these settings. She doesn't say anything about what the message is. There is nothing in the signal about the message itself. And yet, just by setting the teleporter devices to the right settings, Bob is going to get the message without it ever actually being sent, which is kind of amazing. And the reason it works is that there's one very, very important ingredient, that before any of this teleportation is done, Alice and Bob are actually given two entangled particles, let's say, and those two have to be, connected ahead of time in some kind of entanglement. And then if they want to send 1 qubit of information, they would use that pair of entangled particles to do the teleportation. If they want to send, more than 1 qubit, they need more of this entangled pairs. But that's what's doing the heavy lifting, as in there is no need to send the information, because entanglement has already connected the two locations. And that's why you can do this sort of magical thing where without sending information, you're sending information. So that's quantum teleportation.
And how does that relate to the way quantum computers will get involved in this type of quantum communication?
Well, quantum computers are devices that operate on the same properties. So you could have quantum computers where the individual qubits within a computer could perhaps be entangled in various ways. And that would allow even gates or operations to be teleported either within one computer or between locations that are nodes in this bigger quantum internet. There are many possible ways of using this type of quantum communication and quantum ways of sending and receiving information and basically manipulating information. So all of computing is basically about controlling information for certain tasks. So essentially what we are saying here is that things like teleportation, superposition, entanglement, these are like having extra tools in the toolbox for doing tasks that we are already doing, such as communication and calculation, but we are trying to do them better and doing them faster with less resources, hopefully. So that's really how this will all build into our current computing infrastructure. Most likely we'll go to some hybrid format where we'll still be using our regular computers, but they will also be networked in perhaps to quantum computers. That will be like sort of an extra source of computing power going forward.
Shohini, can you just clarify a point there about this very short delay? Because I thought that all of the kerfuffle about entanglement was the fact that these two particles, regardless of how far apart they are, could be galaxies apart. The point is that the change in those two particles is instantaneous. So we're not talking about the time it takes for light to pass. Are you saying that the teleportation is actually dependent on a beam of light passing from one place to another rather than information being encoded in entangled particles at distant points?
Right. So that's a very great question because you're right. There's a lot of there's a subtlety there that entanglement, you're right, seems to be instantaneous. That's what's really magic about it, that when two particles are interacting and they get entangled, after they are entangled, if you separate them out and put them on opposite ends of the universe, each of them are still in some of the strange superposition. We don't know whether particle A is 0 or 1, and we don't know whether particle B is 0 or 1 ahead of time. But the minute we measure particle A to be 0, then because of entanglement, particle B is instantly 0. There is no time lag at that point. It's instant. So that kind of instant sort of cause and effect seems really bizarre because it does seem to violate what we mean by even causality. Absolutely. How does one thing on one end of the universe cause something on the other end of the universe if there's no way to send a signal that fast, which we don't think there is? So that's what caused all of the debate. And people like Einstein got very, very worried about these things. And, he concluded that there was something wrong with quantum mechanics. He could never actually prove that to be true. Eventually, experiments confirmed entanglement really is exactly the way I described it, and that there's no way to, somehow fix up quantum theory to make it work by saying, oh yeah, there's some extra piece that we're missing. In fact, we can test that, and that's actually what won the Nobel Prize this year. Absolutely. The tests of entanglement. Right, mm-hmm. Which confirmed that it really is that weird. But what I meant with teleportation is that even though there's this instant connection between particle A and B, when you try to send a message, meaning a specific message, then you do have to add something to it because particle A and B, remember I said that they are instantly connected. But ahead of time, we don't know whether particle A is 0 or 1. So we can't force it to be what we want it to be. There's a randomness. So you can't actually send a specific message. You can send a random message, sure, instantly. But if you want to send a specific message and control it, then you need that additional beam of light or signal, which tells Bob, who has particle B, that I've measured particle A, but also you need to do something to your device. And then you'll get the message I want to send and not a random message. So that's how, causality is saved in teleportation.
And presumably there needs to be a clear line for a light beam to pass between these two stations. Is that correct?
Absolutely. So if your light beam or your signal, whatever, it doesn't have to be a light beam. It could be an email message or Wi-Fi, whatever. This is just a standard message you send. Ideally, you would want to send it at the speed of light, therefore a light beam. Now, if the light beam gets absorbed or somebody else blocks it or whatever, and it doesn't reach the receiver, then of course teleportation will not work.
Okay, thanks for the clarification there, Shohini. That is a very different way that I had understood, that in some sense the information was being encoded in the qubits itself, maybe just associating their particular movement, spin, charge, whatever it may be, and saying, okay, that particular charge symbolizes that bit of information. But as you say, that would radically limit the amount of information you could encode, wouldn't it? Now,
no, you can encode information in these properties that you mentioned, but you can't teleport it faster than light.
Right.
Because in encoding, once it's quantum encoding, it's in the superposition, and the superposition is probabilistic. So you can't control it ahead of time. It'll be random.
Exactly.
But it is there. You just, have to figure out a way to extract it correctly.
So coming back to the limitations of quantum computer development so far, in our episode in this third series, The World as a Neural Network, with physicist Vitaly Vanchurin at the US National Institute of Health, he talked about how quantum computers were receiving the lion's share of investment, but that the neural network chips that he is in the process of developing promise results a little sooner than the development of quantum computers, suggesting that a real workable quantum computer hasn't yet really been developed. Now, you touched on some of those challenges to overcome earlier. What are the yet to solve problems with this tech that he's referring to? And what's your forecast in terms of the majority of them being solved and this application really being a realistic something we can actually roll out?
So trying to predict the future of any technology is kind of problematic because we always get it wrong. But I'll give it a shot anyway. As I was saying, the single biggest issue is how do we go from the small number of qubits that currently we know how to control in small devices? How do we use those small, tiny processors and then link them up in a chain to build a large scale quantum processor? And when I say large scale, I'm talking about millions of qubits that we can each control individually, each of those millions of qubits, and keep them, isolated from every other object in the universe. So that kind of large-scale quantum computer doesn't exist today, as I said, because of the challenges of keeping the noise down.
Sorry to interject, Shohini, but listeners, we talked about this with Paul Davies in our episode about Einstein, that there many particles can literally pass through entire planets. So you can imagine trying to build a way of actually enclosing that system. Almost impossible, I imagine.
Pretty much, exactly. So I always admire, real world engineers and the incredibly creative ways they find to be able to build anything, even remotely close to being isolated at the level we need it. Keep in mind, of course, we don't need it to be isolated all the time, just during the computation. So that's one of the windows we have of opportunity. So if you can make this computation fast enough, maybe on the order of, I don't know, seconds, then perhaps you can, keep the system isolated for around, during that time. And we're nowhere near seconds, by the way. We're talking about milliseconds right now. So it's a long way to go. However, that's part of the specific questions that need to be answered in order to scale up technologies. And to give you a sense of where we are now, as I said, we're talking about trying to scale up to computers that have millions of qubits. And state of the art recently, IBM announced that they have built probably the largest, most powerful quantum computer as yet to be built, and they have about 400 qubits. So we are, many, many orders of magnitude away from where we need to be. However, progress has been stunningly impressive because back when I was just starting out in grad school, quantum computing was, an area that people were excited about, but there was nowhere near the level of interest and funding and development, certainly on the industry side, that we see today. So it was not even part of the conversation at all. And that wasn't that long ago. And here we are now with actual working small scale quantum computers. They're not necessarily perfect. There's a lot of errors in them, but they actually exist. They did not exist when I was in graduate school, for sure. So to me, that's really exciting and gives me hope. And as I said, human beings are very, very creative, especially when they're given a particular problem to solve. So I think in the near term, maybe in the next decade or so, we will probably see at least one or two examples of problems, especially in areas like quantum simulation that I was talking about, things like understanding the chemistry of certain molecules or things like this, where we will see perhaps a problem being solved that we have not been able to solve before. And then I'd say going up to those millions of qubit kind of quantum computers, that will take much longer if we can solve these very significant problems. Or we will find that there is no solution. One way or the other, I think we will know much more within the next decade.
Excellent. So moving on to our second main topic of today, Shohini, women in science, or the lack thereof. For myself, as a conscientious amateur journalist looking to represent equally the voices of male and female scientists, I found a real inequality between the signal being amplified from male scientists and the female scientists. And that makes it really hard to cover the topics I want to get out there on the show without speaking to an overwhelming majority of male scientists. And I assure you, I really have tried. Listeners, I'm working on this constantly, so be reassured. It's not something that's off my radar. Perhaps we can start, Shohini, with you telling us about your new book, Her Space, Her Time, and the history of extraordinary female scientists who have excelled in their fields, only to have their work appropriated, to put it mildly, by their male supervisors, perhaps most visibly in the awarding of Nobel Prizes. And then maybe you can just tell us the success story of campaigners like yourself that's leading to this slow change in the way this story is unfolding.
Sure. First of all, thank you for your efforts to try to address this issue and to also raise awareness about it. Surprisingly, although this has been an issue for a long time, it's not necessarily as talked about as I at least would like it to be, which is why I decided to write a whole book about it. This is the new book, Her Space, Her Time. And this is a book focused on physicists, because being a physicist myself, I really wanted to, focus in on this area. And physics is actually one of the fields where the lack of women has been one of the worst, as in we're still at maybe, around 20% or 1 in 5 currently physicists and physics students are women. And we don't even go beyond the binary as yet. So gender diverse representation is even worse. But going forward, hopefully those numbers will change, although they've been sort of roughly at that for a very, very long time. One of the reasons, as you mentioned, is that women have always been contributing to physics, but they're not necessarily acknowledged. In fact, it's so common, it's called the Mathilda effect, when somebody else gets credit for women's work. So what I wanted to do is address that issue and shine a light on the fact that not only 1 or 2 women, or they're not just exceptional women who have contributed to physics, but there's been so many. In almost every major discovery, there have been women who have contributed, but we don't know of their contributions. So I wanted to tell the story of physics from that perspective, where I talk about all the different physics discoveries and sort of go through the stories behind them, and also highlight who are these women, and they've transformed our understanding, whether you're talking about dark matter or our space exploration program, or understanding the beginning of the universe, the Big Bang. All these major discoveries have been made through some huge contributions by women. So that's what the book is about.
Can you give us an example? I think she's got another brilliant TED Talk, listeners, on this. Maybe give us an example from your talk where there was some Indian female scientists. I think it was around the time of the Second World War. Tell us about those 2 ladies whose work was more or less stolen by their supervisors?
Well, not quite, but yeah. So the woman that I highlight in Her Space, Her Time from India, and there are women actually from all around the world that I wanted to include. In fact, it was hard to actually narrow it down. There are that many women out there. So the one from India that I talk about is Bibha Chaudhary, and she was one of the rare women in India back in the time of right around just before the war, back in the time when this was pre-independence India, where it was quite a challenge to aim for higher education, and certainly a challenge if you were a woman. But she stuck to her guns, and she got a bachelor's degree in physics in India, and then she was working with another colleague, her supervisor in India, and they were working on trying to observe and see what they could explore about cosmic rays, which are basically these high energy particles that are always hitting the atmosphere of the Earth, just coming from outer space. So they had a way of detecting these particles. In fact, the detection process that they were using was actually invented by another woman who was an Austrian woman named Marietta Blau, who I also describe and talk about in the book. But so Bibha Chaudhary and her supervisor were exploring cosmic rays using this technique, and they, in fact, ended up discovering these new particles, and used a technique that they themselves developed to try to explore the properties of these particles and show that this was a new particle. And their discoveries were so important and so new that they published a whole series of papers in the journal Nature, which, as we know, is probably the top science journal. To have multiple papers in that journal is a huge achievement. But then it was right around the early 40s, because of the war, they couldn't get equipment, materials, so they quit. And eventually, a few years later, after the war, a British scientist, Cecil Powell, actually used exactly their techniques, and he did reference their work, but he used their techniques to do the exact same kind of experiments and discovered this new particle more convincingly. And this was, in fact, the discovery of the pion, and that led to him winning the Nobel Prize. But Bibha Chaudhary and her supervisor Bose were both, of course, not part of that story. So this is one of many such examples. But Chaudhary went on actually to be involved in the discovery of the neutrino as well, which because of discovering one particle is not enough. But she also did other excellent kinds of work throughout her career, but never found acknowledgement throughout her life. And only recently is her work being more discovered. So I really want to celebrate her.
And the Nobel Prize is right at the center of this whole sort of male-dominated feel of the business. And I wondered how you feel when a respected institution like the Nobel Prize Committee, for so long, really permitting the appropriation of female co-authors' work, for the credit to be then taken by their supervisors, almost always men. Now, how do you feel that they've started to give out a few prizes to women? As if it's almost a sort of tokenism as part of a sort of following a cultural change. Do you think it goes far enough, that what feels to me a bit like tokenism, or is it simply just sort of throwing a few scraps to justify a continuation of male dominance in this field?
That's a fantastic question, because you're exactly right. I struggle all the time with things like not just the Nobel Prize but awards in general, because it's not just the Nobel. Awards are usually skewed, and the way we evaluate criteria, even the criteria themselves, are part of some existing norms based on privileged structures, and we have to question everything about awards anyway. But with the Nobel Committee itself, it's not just that they perhaps were, contributed to this sort of bias, but they actively actually ignored women, in the sense that there were women who were nominated over and over and over again. One of them being Lisa Meitner, who discovered nuclear fission, and just like with Bibha Chaudhary, it was her colleague Otto Hahn who got the Nobel Prize. But she was nominated dozens of times, and the Nobel Committee never acknowledged her work. So this was more than just them not being aware or, just going with perhaps inadvertently ignoring women. This was, actively promoting this level of bias. So this is why I personally, I do have, lots of conflicting thoughts about the Nobel Prize. Perhaps it's time to just end it and restart with something that's better and doesn't have this history that is biased. And your point about at this point can be corrected by selecting a few token awards. Firstly, even when they're not token, it's hard now to actually separate out what is tokenism and what is real. And I know that in my own career, every time I get a grant or I get some award, I think, wait, did they give that to me because I'm a woman? And that's a terrible feeling to have. So I don't know anymore whether it's my work or whether it's my gender. And that's not a question that men tend to have to ask. And so this is another aspect of why I think awards in general are very problematic. And to be honest, a lot of work is done based on other people's work or done as a group. So singling out one person to celebrate, I know we love to celebrate, great achievements, but maybe there's other ways. I don't know what would be better. Maybe we need to acknowledge the group or, the work itself and all the people who contribute to it. But the way we're doing it now doesn't seem very, very inclusive.
Part of my idea for the solution to our sort of neoliberal tokenism regarding race and gender is maybe just remove the image and the name from the paper, so they're just people. And in that sense, the publications, Nature, all the big publications wouldn't have that even in mind, and they could just say, well, listen, actually we don't even know the gender of the people who are on this paper, and we've just chosen it because it was good work. That might just take us away from this tokenism, which obviously is a step in the right direction. Don't get me wrong, listeners, obviously we need these people to be represented, but if it is just tokenism, is that really the kind of equality we're looking for? Now, you mentioned this interesting fact that 1 in 5 physicists are women, and it has been like that for a long time. Now, some commentators, evolutionary biologists, have controversially argued that women are just less likely, looking at a probability distribution of the population, to be drawn to a career in something like physics, and would be more likely to be drawn to other careers. And they argue that this explains the lack of women in science and therefore their lack of recognition. But that kind of flies in the face of some of the women scientists you've just been referring to. I mean, a lower proportion of women in science doesn't mean that lower proportion deserve any less recognition. So what are your thoughts on this kind of, lower proportion, therefore lower recognition argument? It seems like a bit of a get out of jail free card to me.
Yeah. So just to get back to your first point about women just choose different careers and have different interests and so on. I'm a scientist. So when somebody makes a statement like that, my question is, I agree. Shouldn't we actually verify if that's the case or not? Meaning, if all else were equal, meaning there aren't, whatever skewed sorts of biases, or the environment is exactly inclusive to the level we need it to be. When we include everybody and give everybody the same equal opportunity to make a choice, what choice would they actually make? Shouldn't we test it? And then we would know for sure whether women choose differently from men or not. So I say to all those people who think that's the case, prove it. Let's see if we really have differences. And that would get us, in order to do that, guess what we have to do? First, we have to build an inclusive environment. So I think those who want to prove their point that there's a difference should be the ones leading the efforts to build inclusive environments, to be honest. Otherwise, they're never going to be able to prove their point. The second point I want to make is that there are actually some studies about whether or not women make choices based on their interests or not. For example, within physics, there has been this global survey of physicists, including men, women, everybody, and from around the world. So we're talking about thousands of physicists who've actually responded to this survey. And there's been multiple rounds of this survey. And what's really interesting, the findings are not surprising in the sense that women are more likely to report doing, most of the childcare and housework, less likely to be advancing fast in their careers, less likely to be getting resources, awards. All of that confirms that there are workplace-related barriers for women. But here's what I want to point out, which relates to this question of choice. Why would women who already clearly have all these challenges, why would we continue in this field? I'm one of those, and I've certainly faced my share of challenges, which I don't see my male colleagues facing. So why do we continue? That question was also asked. Why do you choose physics? Because we love it. So the idea that somehow physics is not something that interests women and that we wouldn't choose it is not borne out by the actual studies. And I think it's similar in many other areas of science. And in fact, it's quite the opposite. It's saying we love it so much that we will do it even with all these barriers. So those are 2 points I just want to bring out, that if we want to talk about women versus men and acknowledgement and recognition, that comes later. Let's first build that inclusive environment. Let's see who actually chooses to do science. And then let's see what would be the impact of that science and who would be the ones celebrated and recognized if all else were equal. So I think in the end, we have to be able to build that environment to understand how we do science, what our choices are.
Yeah, and such valid points about sort of cultural biases, about lifestyle biases coming into this right from the start of when children are going to school. But even if it did turn out with a probability distribution, a bell curve of the population, even if it did stay around 1 in 5, or maybe even 2 or 3 in 5, then we'd still have this same question about recognition. Surely if it's 1 in 5, 1 in 5 of these recognized brilliant people should be women. And this idea that there's less people, therefore there's less prizes going out, again, just doesn't quite add up for me. Anything to add on that, Shohini?
Yeah, that's, for one thing, I don't think that's even really what happens, as in when there's 1 in 5 men in a certain field, it's still the man who gets the recognition. So when you flip it around, for example, let's look at something like, chefs in restaurants.
Hairdressers.
The fact is that there are many more women who cook, by the way. We just don't call them chefs. But when you include all of the women out there in restaurants versus men, in these areas, it's still the men who get the credit, regardless of whether it's seen as a women's field or not. So it's not the case that the reason women get less credit is when their proportions are less. That is actually not even true if you really examine it, because there are areas where men are, fewer in number and still get all of the power and the credit. So that's why I don't believe in this argument at all. It's just a made-up thing that is used to justify bias.
Absolutely. Well, Shohini, thank you for that little insight. And listeners, anybody who's interested in all of these topics, luckily it's not just in science that this conversation is coming to the fore. It's across all fields, including politics, and the ones Shohini was mentioning there, things that are traditionally more, populated by women. But let's come back to another of your books, to come back to quantum strangeness. Let's come to your other book, Clues to the Cosmos, which sets out to sort of chart the great scientific discoveries in physics and sort of follow the clues like a detective that have advanced our understanding of the universe. Perhaps you can give us an example from the book of the unfolding of one of these great mysteries, and perhaps an example from your own work in quantum physics, because obviously the implications of quantum physics are such a central part to this show. Give us an example from that book.
Yeah, sure. In fact, the story of quantum physics, surprisingly, is extremely old. It's not just some modern theory. I would say it traces the beginnings back to, couple of thousand years ago, when we first started thinking about things like what is sunlight, and how do we see things. So the study of light was actually one of the first steps towards building the theory of quantum mechanics. And for a long time, people did experiments. The ancient Greeks did experiments. Euclid came up with laws of how light travels on straight lines and so on. And then there were some very, very important discoveries and very detailed studies of how the eye works and how we see things and the properties of light by Arab scientists. And there is a very famous book on optics written by an Arab scholar. And that actually got translated and was distributed all over Europe. That led to people like Newton and others in Europe starting to think about light in interesting ways. And this led to developing and realizing, light travels in, it has this wave property. There's frequencies and wavelengths of light, which are basically lead to different colors of light and things like this. And that sort of was a field that grew for a long time. We could understand how light works, control it. We started building mirrors and prisms and, really understanding and controlling, manipulating light. But then suddenly, and this is how all science works, and this is how the book traces out different discoveries. Discoveries happen when actually old science fails. So in this case, this idea of, light waves and wavelengths and energy, all of that was so well understood. We were like, yes, we really understand light. And then along comes this experiment where, the light is shining on a particular sort of metal surface, leads to some current which people couldn't understand because it just didn't fit this sort of story of light as a wave. And it just none of the predictions actually worked. So basically it broke our theory. And whenever an experiment breaks theory, that's like really, really kind of shocking, but also really exciting, because then you can think up new theories. And that's in fact what led Einstein to come up with a new idea about light not just being a wave, but particles, packets of energy. And that's what he called a photon. And this, in fact, was the discovery that won him his Nobel Prize. Okay, so we're not really going to go back into the Nobel debate, but that's actually what got him the recognition, not his relativity theory, although that should have won a Nobel Prize. Anyway, so from that, we started really understanding that light is this really interesting, complex thing, both wave and particle. Somehow we needed to describe it in a more holistic, fluid way. And that led to fundamental equations that became the sort of the foundations of quantum theory. And Schrödinger was, of course, one of the key players in building that kind of mathematics, as was Heisenberg and many other scientists along the way. And so the story, as you see, it keeps evolving and growing. And in recent times is when we started realizing, wait, we can also describe not just light, but matter and everything in this quantum structure, and think about it as information. Particles now became particles of information. And this led us to this new way of quantum computing and quantum information theory. So what's the next step? Who knows? We basically have to break the theory by maybe making a discovery where the quantum mechanics doesn't quite work. And then maybe we will be able to get to the next step of this evolving story. I don't think we're at the end, because that would be kind of boring. But so far, quantum theory is the best tested theory ever in history, and it's kind of withstood all of our experiments. So we don't really know how to break it, which is why we don't make progress on questions like entanglement as yet. But it's exciting times. So part of what I do is think about what are these pieces of entanglement? What is quantum theory all about? And what's quantum about quantum? So that's what excites me. And that's why these stories are so amazing, because it's such a wonderful story of discovery. And some of it is accidental. Some of it is, about being creative and imaginative, but it's all really, really exciting.
Well, and it's really interesting that I'd never really thought about it, that this particular discovery of photons led to the famous wave particle experiments, which of course was where it all kicked off and where this totally new type of mathematics had to be brought to the fore. So I want to close, Shohini, by asking you maybe the big one. I think it is an important question to ask. In your opinion, coming face to face with this phenomenon of quantum strangeness in your daily life, what are the implications for the fundamental nature of reality? And perhaps here we should bear in mind, the 2022 Nobel Prize, which basically has proved that local realism can't be true, that we can't have both local and real at the same time. What are the implications of that? What's your take on this? Because obviously there's so many different interpretations of quantum mechanics. What's your feeling about what this tells us about the nature of reality?
Wow, that really is a big question, isn't it?
It's the big question, isn't it, really, in your field anyway?
Exactly. So basically it comes down to, are you my dream or am I your dream, in a sense? As in, what is reality itself? Well, we certainly know that it isn't the sort of fixed macro real reality that we usually mean. We know for sure. That's exactly as you were mentioning, this year's Nobel, as well as all the work that led up to it, actually proves it beyond any doubt that we cannot be talking about something that exists and has this, causal structure that makes sense based on our own experiences. The underlying quantum world is, as I was saying, much more fluid in the sense that, does it really exist before we observe it? We don't really know. And it might be that our theory is really just the description of our information rather than what it really is, if there's even such a thing as really. We're stuck with this sort of mathematical framework, which seems to work beautifully. And it's precisely, as I said, we've tested this over and over again. All of our experiments agree with the predictions of quantum mechanics. So there must be something to it. But when we do the observation, the question is, what layer of reality are we observing? Is it, somehow that it's just some description of our information and that's, don't ask anything beyond that? Or is there something beyond what we measure that's real and exists, whether or not we measure? Seems like there isn't. And that's a very, very sort of disturbing, perhaps, way to think of the universe. But on the other hand, maybe it means that things are not fixed, which means we can be more, adaptable and changeable. It is a philosophical question, you're right. There's not really a way to know for sure what's the right interpretation, because the observations will be the same, whether you interpret it to be that there's no reality, or that it's your dream or my dream, or whether it's, that we're all in the matrix. No matter what your interpretation is, what you observe will be the same. So how do you tell the difference? One of the things as a scientist I'd love is if we could figure out, okay, here's one interpretation, which, for example, many worlds, there are many, many different universes, and each one, there's some version of us. Is there a way to test that? What if we could test one of those interpretations and compare it to another one? That's kind of what is the area that called quantum foundations. People think about these things. But so far, there hasn't been a lot of progress in terms of really being able to narrow it down to see, like, this is the true interpretation versus whatever. The matrix is not the true interpretation. Who knows? But they're big questions and fun. But yeah, I don't know the answers, what I'm trying to say.
What about observers, Shohini? I mean, there's an important point here about macro systems, isn't there? That an observer, whether it's a person or an instrument, whatever that observing device or being is, they are interfering with a microsystem. And in that sense, they're disturbing the fine balance of that entanglement. Now, is that the way you would see the measurement problem, that it's about macro getting involved in micro? Or do you think there's a more profound implication to these strange interferences when measurements take place?
Well, it's definitely not just about macro versus micro, because that sort of line that you draw, what is micro versus macro, we can actually move that. As we get better at controlling quantum systems, we can actually take not just one particle, but take two particles and make that, define that to be micro. And then anything beyond that, we say macro and observation. But then we throw in another particle, a third particle. Now that's micro. And then the fourth layer is macro, and so on. And we've done that to the point where now you can see quantum behavior, meaning that micro system that we call quantum. We can see quantum behavior even when we're talking about, collections of millions. I mean, macro level objects can actually be considered quantum micro. So the border between micro and macro seems to be very, very movable. So that can't be the answer, is what I'm saying. The measurement problem is a problem because, in fact, that's the one thing that's not described within quantum theory. Meaning that we know how to describe this bizarre thing called superposition and entanglement using very precise mathematics. And we know how to describe what happens after we measure it. So we have this superposition with probabilities of different outcomes. And then after we measure it, of course, we get a particular outcome. So we know for sure we have it. And at that point, we pick up the quantum mathematics again. Between that gray area where we have just possibilities, and then from there to doing the actual measurement and how those possibilities become one particular outcome, that's not actually described within quantum mechanics. Something happens and then it's projected, that collapse. So because it's not part of the theory, we don't know how to test it. There are experiments being done to see, can we actually follow or observe the particle as it's collapsing? And these are very cutting edge, very difficult experiments. Maybe we'll find out more about it. But it's something that, because it's outside the theory, it's very confusing. And we do need to maybe broaden our theory to try to explain that better. I don't know what the answer is, but right now the answer is something happens.
Well, Shohini, thank you so much for your insights. Listeners, you must go off, take a look at this wonderful story, Clues to the Cosmos, this story of this. It's sort of set up like a detective story that slowly unfolds these clues that get us to where we are as a scientific community. And also, please go and check out this new book, Her Space, Her Time, a very, very important issue, something that we really, really want to push more and more into the scientific community so that women can really just be heard as normal scientists without there really having to be all of this issue around it. And it leaves me just to thank you, Shohini, for being so generous with your time, wishing you all the very best with that book and with the continuation of your campaign and the continuation of trying to pin down those naughty particles that keep flying into your systems and disturbing your calculations.
Thank you so much, Freddie, for everything that you're doing as well, for all of these wonderful questions, and for having me on your show.
That's very kind. Take care, Shohini. Bye-bye.